Before we go inside,
Yeah.
could you tell us a little bit about the tiles?
Well, it's made of these two different shapes, a fat rhombus and a thin rhombus, and they steel stripes on them have to match. And if you make them match, the only way you can fit them together is in a pattern which never repeats. You could go on to infinity, but it never repeats. Well, time is, if you like, the most precisely measured physical quantity. Time from the Big Bang, if you like, till now is known. Well, no, I don't mean to say that time is known precisely. What I mean is that clocks are that accurate that over that period of time, they would still be precise to a tiny fraction of a second. However, and I think this is the point you're probably raising, there is this question of our perception of the passage of time. Now, that doesn't really fit in with physics in a way, because the view I've been talking about with general relativity, Einstein's theory of gravity and curved space and all that, precise time measurements and precise time notions and the theory of how it works are extraordinarily precise to many, many decimal places, something like 15 decimal places. So extraordinarily well understood. However, this picture is of sometimes what people call a block universe. It's a four-dimensional space and time out there. It's just there. And there's no feeling of a passage of time that we experience directly, that somehow time flows. It's not the same as space. Space is just there, and time seems to flow, and things change and all that. And that conscious feeling of the passage of time is not really understood in physical terms at all. So I do regard it as there being a big mystery which is connected with the phenomenon of consciousness, which has to do with what is the passage of time, not the physical time which we do understand extraordinarily well. The reason that human beings can sometimes go beyond the computers is that they make mistakes. But I find that as an unconvincing reason, because in the first place, it's very easy to make computers make mistakes. And that's, I mean, if it's our advantage to make mistakes, then, okay, we make the computers make mistakes too, and they're still computers. I think that there is a quality which involves consciousness, and the quality of understanding something involves consciousness, and is something which is beyond putting on a computer. I mean, as we use computers now, it's admitted they don't understand what they're doing. I mean, you put the rules in, and you interpret what the rules mean. Okay, it can be very complicated calculations, but you know what it's doing. You don't know the implications of all the details, but you know the meaning of what it's doing. Whereas it doesn't have any concept of meaning, doesn't have any concept of understanding. These concepts are things which require our awareness. Now, it's a very mysterious thing, because I don't know how to formalize that, and it's almost impossible to formalize, because formalizing it almost means you could put it on a computer. So if you formalized it, you've missed the point. I think that the issue of pinning down consciousness is a bit like this, or like understanding, you see. This is the thing I try to say, that you get round the girdle argument, because your understanding is a slippery thing somehow, and you can sometimes bring in something that wasn't part of it before. And it's a bit like you can't grab it in that way, because once you think you've got it, you really haven't. And it has very much that character. Because if you think you can formalize it in some system of logical constraints, then that very process has let it escape, in a sense.
Probably next year, a new book, the title of the book.
This one is called, rather brashly, Fashion, Faith and Fantasy in the New Physics of the Universe, where I try to point out that some of the common beliefs in physics, which are currently very much followed, maybe there are some things to worry about what people are doing. I mean, this was a book that was commissioned by the Princeton University Press. About 11 years ago, I gave 3 talks in Princeton at the behest of the press, and they wanted me to give a title, so I suggested this title rather rashly, without thinking about it very much, which to some extent was making some somewhat negative comments about some of the very active things going on in physics departments in Princeton, as well as many other places. So it was probably a bit of a stupid thing to do. Nevertheless, as time has progressed, not surprisingly, things have changed somewhat. So actually, somewhat surprisingly, they didn't change as much as one might. I was worried that the fashionable ideas would cease to be fashionable, because it was primarily, well, it was string theory, but not so much string theory as such, which I don't have any problem with as an idea. It's what I objected to was the necessity that string theory had found itself to be driven in a certain direction, which was that there are, they claim, extra dimensions. That space, you may be familiar with the 3 dimensions of space, so this one, this one, and this one. But the idea is that hidden, there are a lot of extra space dimensions, and these would be all in a tiny, kind of wrapped up in a tiny extra dimensions that would not be visible to us because they're so wrapped up, very small. But I have a lot of problems with that, which I don't believe can be right, you see. But since it's such a big topic, and still remains this, I mean, there are many advances in theoretical physics are very much tied up with this idea of extra space dimensions. It's an intriguing idea, but I don't believe it works. When I first heard about string theory, I thought the idea was a very elegant and maybe important one in physics. I mean, ideas can be very elegant and beautiful mathematically, and it turned out not to have any relevance in physics. and people get confused by these things sometimes. I mean, when you hit the truth, it seems to be, it does have an elegance. I mean, that's what we've experienced in the great theories which have been successful. They have a certain mathematical elegance, and they fit together in a way which is often surprising and beautiful. But that in itself is not enough. I mean, you may find an idea which mathematically is very elegant. I think one of the most striking examples is when the great Irish mathematician Hamilton, who was very important in physics, I mean, the notion of a Hamiltonian based on his ideas is fundamental to quantum mechanics and to other areas. But later in his second part of his life, later in his life, he made a very wonderful discovery, mathematical discovery, things which we call quaternions. These are numbers which have very elegant properties. And he thought these were so beautiful that the whole of physics must be built from these ideas. And he spent the later years of his life just devoting himself to this subject, which is very beautiful in many ways, and has had an influence in certain slightly indirect ways in physics. But it certainly did not have this fundamental role that he thought. So you can be distracted by ideas and a greater importance than perhaps they should have just through their mathematical elegance. So you have to be careful, you see. String theory is a big idea in that it's very fashionable, but there is no evidence, I would say no evidence, that it has any relevance to physics at a deep level. Okay, there may be the odd way in which string ideas can be related to genuine physics, but it does not seem to be. I mean, it might be that it does have deep relevance to physics, but there's no evidence of this. Whereas the next, you see, that was the fashion. It's still a very fashionable idea, even though it does not have any support from observational physics. It's not quite so fashionable as it was, but people still talk about these higher dimensions all the time. You see. The higher dimensions is not, you see, string theory doesn't need higher dimensions. It's just that the way in which the subject developed, they were driven into having higher dimensions. And that's what I'm complaining about. It's not the string idea originally, it's where it was driven and into higher dimensions. And that was the first chapter of Fashion, Faith and Fantasy. That's the fashion. Now the next idea, which I am worrying about, is something completely different because it has an enormous support from physics. And that is quantum mechanics. Now you see, quantum mechanics is, well, fashionable, clearly, because it has an enormous support from physics. But what I'm attacking is not that, but that quantum mechanics is regarded, it's become a faith. And that is to say that people accept the rules of quantum mechanics at all levels. Now, where quantum mechanics has a great deal of support in physics is small things. You talk about atoms, molecules, fundamental particles, the basic things which, if you like, lie at the roots of our physical understanding of objects. And that is, when you really get down to it, you have to understand about quantum mechanics. Quantum mechanics is what governs the way things behave. But then this has become a faith, and people take this as holding at all levels. And, well, the famous example that Schrödinger himself, who was the originator of the fundamental equation that governs quantum mechanics, the Schrödinger equation, and this equation is based on certain ideas which are fundamental to quantum mechanics. Now, one of these basic ideas is the superposition principle. So that says if one thing, it can be here, or it could be in another place, then it could be a state in which it's in both places at the same time. And you see, this could be a particle, could be a neutron. There are experiments with neutrons in which the neutrons could take two different routes, and if they're allowed to take two different routes, then a certain kind of pattern occurs, interference between those routes. The two routes interfere with each other in subtle ways. And so if you close off one route, then these effects disappear. Mm-hmm. You say, well, it just went the other way. Close off this route, you say it just went this way. But if you have both routes open, then it does things which depend on both routes taking place simultaneously. So, and that's a universal principle in quantum mechanics, that if a thing can be in one place, or it can be in another place, then it could also be simultaneously in both places. And it's very easy to make experiments in which this happens. Now, it happens for protons, neutrons, individual particles, It happens for molecules. There are these very elegant experiments that Anton Zeilinger in Vienna did, which show that these things called buckyballs, these are little molecules which contain many, many carbon atoms. And they have a very beautiful symmetry, and you send them through two slits at once, and you get these effects. You say, well, even for those molecules, they can be in two places at once. So the faith is then developed that this holds for any scale. And the equations say that. So if you believe the equations, then you must believe that things can be in two places at once. Well, you see, part 2 of the book is very largely conventional quantum mechanics. I try to explain these ideas, you see. It's only at the end I bring out the problem. The problem was, well, I mentioned the problem earlier in the book, but I only really tackle it at the end of the 2nd chapter, which is the faith chapter. You see, Schrödinger himself was very careful to point out the problems with his own equation. So he said, there's a very famous, the thing he's most famous for in the public imagination is his Schrödinger's cat. So he says you could have a cat, you could make an experiment where you have a cat which could be alive or it could be dead, but you make a state in which it's both dead and alive at the same time. And the equations will say, yes, you could have a cat that was dead and alive at the same time. And Schrödinger was pointing this out. He said, look, I could make an experiment where a cat was dead and alive at the same time. You put it in a box, you see, and you don't know what's happening in the box. And the box, your equations say that cat must be dead and alive at the same time. And Schrödinger was making this example to say, look, this is ridiculous. The cat would not be dead and alive simultaneously. But people kind of believe the experiment rather than what he was trying to demonstrate. He was trying to demonstrate that this is absurd. And so there is something we don't understand, something beyond what his equation tells us about the world. And I'm agreeing with Schrödinger, you see. I'm not agreeing with the cat because he was making the cat do something which wouldn't happen. But it's not a difficult experiment. Okay, not a very humane experiment, but it was meant to be a thought experiment, not a real experiment, you see. But you could do it. And what would happen? Do you open the box and you look inside? This is what many people argue now, you see. Many people take what's called the many worlds view. They say, well, okay, you do an experiment, and in this box there is a superposition of a dead and a live cat. You open the box and look inside, what do you see? Well, according to the Schrödinger equation, if you believe it sort of right up to the level of cats and people, then you say, you are now in a superposition. One part of you sees the live cat, another part of you sees the dead cat. And these two instances of yourself occupy two parallel universes, is the picture, you see. So they have what's called a many worlds view, and there is one instance of you seeing the dead cat and one instance of you seeing the live cat. Well, I think this is way too taking this to extremes, which I just don't believe. But it's surprising how many people accept that picture, and they say, oh, well, there must be parallel universes with the same, different people doing, the same people doing different things. Yeah. There's these people hold very strong views, and it's very difficult to shift people from one view to another view. What do you see? You can take the logic, even though the logic seems to lead you to an absurdity, as in this case. Nevertheless, people say, well, we must accept quantum mechanics. There is no experiment which refutes quantum mechanics, so we must accept it at this level. I mean, I say that's absurd because there is no experiment which gets anywhere close to the level at which you might expect to see deviations. Well, actually, that's not quite a fair statement. There are experiments now which are approaching this level. That is to say, there are currently experiments being performed which might be able to see where quantum mechanics goes wrong. But in my view, it is that quantum mechanics goes wrong. In Schrödinger's view, it was that quantum mechanics goes wrong. In Einstein's view, it was that quantum mechanics goes wrong. In Dirac's view, this is even more surprising, because Dirac was the physicist, mathematical physicist, an English physicist, who formulated the general framework of quantum mechanics as it is now accepted. But he had his doubts. He says, look, this is not the final answer. There must be at some level, some new theory which goes beyond what we understand now.
Invented, or I should say discovered, the tribe.
Well, other people have things a bit similar. But the idea is you have something which would be impossible to build, but you could have a picture. So that it's consistent locally, but as a whole, it doesn't work. See, I showed my father the tribar, and he then did some buildings. A staircase which went up all the way. You kept going round and round and round, up all the time or down all the time, depending which way you went. And we wrote an article giving reference to Escher's work, and then he used both of these in pictures of his own. The staircase was in ascending and descending, with the monks going around.
Correct, yeah.
Two directions. And the tribar he developed into the waterfall. Yeah.
Could I ask you what this is?
That's my mousetrap.
You did this yourself, right?
That's a mousetrap I made some while back, yes.
And it's
a
works?
humane mousetrap.
Humane. It doesn't kill them, it just captures them, right?
That's right.
And what do you
It's got the mechanism inside, which is made out of a mousetrap that kills a mouse.
Mm-hmm.
But this simply closes the door. They crawl in there, get some food, chocolate particularly, which they like, and unfortunately, the door closes.
And then you take them outside?
I take them a long way down. I used to take them just down the end of the garden, but they can't come back. No, they're good at that. So I take them a long way away.
So you have time for this?
No, I made that ages ago. But that was my reserve one. You can get commercial ones, but these are made of plastic. And some of the mice learn how to chew their way out.
Out of plastic, so this is better.
So I made that, only when they chew their way out of the other, then I would bring this one out. This is my last resort trap.
What I mentioned when we were walking, strolling through the woods, we passed supposedly a river, and you said jokingly you call it the Twister.
The river Twister. Well, the joke is that it's a bit of a miserable-looking river which hasn't actually done too much yet.
But there's a theory that you worked on, and you told me you're still working on. It was the Twister theory.
Yes. Well, that goes back to goodness knows. I've forgotten how long ago it was.
What does it deal
about
with?
50 years ago. About half a century.
But you remember it.
Oh yeah. What does it do? Well, it's become quite important in certain approaches to high-energy physics, when people scatter very high-energy particles off each other. But it's not designed for that. It's a different way of looking at space-time structure.
I see.
But it directly handles particles which have no mass, like photons.
see, particles of light. But if you have very high energy particles, then they behave as though they had no mass. You see, as long as the energy is high enough, then the rest mass, E equals mc squared, gives the mass gives it an energy. But if they're more energetic through their motions, kinetic energy, far more than the rest mass, then they become in effect without any mass. And so the formalism which I developed almost, well, something like half a century ago, has been found useful in doing calculations for scattering of massless particles. But the idea of twistor theory is much broader than that. It's a way of looking at physics in a very much more general way.
You mentioned something in one of the discussions I heard on physics, that it's become sort of a religion and that something needs to be changed. Am I wrong here?
But this was, you're thinking about the faith in fashion faith and
right, yeah, but
well, that's primarily quantum mechanics, but it's not that it's not meant to be comparing it with a religion really, but it's saying it is a bit like religion
okay.
In that people take it as dogma, which is handed down, rather than something that you have to think through, and does the dogma extend to the lengths that one uses it. So in quantum mechanics, the case is that I think there are limits to the scale at which it operates. And for things which involve too much mass displacement, then I think the theory that we now know doesn't give us an answer. I think we need something more. And twistor theory, one of its aims is in that direction, giving a formalism which would be able to extend beyond current quantum mechanics. But at the moment, it combines ideas from quantum mechanics as we know it, and relativity, special relativity, which is just involving when speeds get close to the speed of light, or general relativity when you have mass causing curvature of space-time. And that's more interesting to me now. There are even recent developments in twistor theory over the last year and a half or so, which give promise to overcome essential hurdles which have been holding us up for about 40 years in the subject. But there wasn't much attention paid to this subject in the physics community. There was some in the mathematics community, but not much in the physics community. But this changed very much in 2003, 2004, when Edward Witten got involved, because he realized you could use twistor theory in ways which combined with some ideas from string theory, and that has become quite an active area.
So do we have to always wait for a long, when you discover something?
Well, I hope
we have
not
to wait.
long. Well, some ideas in mathematics, you wait a lot longer than that.
Yeah.
But that's not the idea. I was hoping people would pick up on it a long time ago. But I mean, it hadn't become that relevant until particles of that high energy where you don't have to worry about the mass. I mean, that's fairly recent in technology, you know, the Large Hadron Collider, the LHC and so on, which they actually use calculations which twistor theory is useful for. I mean, they have other methods too, but some of the techniques would involve having a big fat book of computer calculations, whereas now you can do some of these things on the back of an envelope. So it's very, but that's technical. You see, it's a technical advantage to use these things. It's not as though you necessarily have a different view of the physical laws. Whereas twistor theory, really its deeper aims are to give you a different way of describing physics.
I see.
The idea is that the point, you see,
It's
normally
a tool. It's a tool.
Well, it's also a, you can't draw a line here. It's both a tool. I mean, that's the way it is at the moment. It's a tool, yes. But the idea is that it's also a different way of looking at physics. You see, I can even say a bit more. You see, normally we think of space. It's made up of points, you see. An individual point is this basic element in space. And if you have a line, that's made up of a lot of points, you see, lined up. But in twistor theory, you take the whole entire history of a massless particle, say a photon. Photon would be a track through space-time. And that entire track is the single element. in twistor theory.
Yes.
And it's twistor because it's got it's got a spin too, and that's a crucial thing to it. It's not just a line; it's got a kind of helicity to it, and it forms a very nice mathematical structure. And this mathematical structure, you can rephrase all your physics into that language, which there had been for about 40 years a big block doing this. And only recently, when I say recently, I mean within the last year and a half, a new way of looking at it which seems to get round that blockage. So this is quite new stuff.
What I understand is, aside from being this Matthew Arnold field, there's an anecdote about Boar's Hill. And you mentioned it to me last time I was here.
I mean, it's presumably a myth, I don't know, but there used to be boars around in this area. I presume there probably were, but I mean, the myth is that the last boar that was ever known to be in this area, there was a student who was walking around in this area, and he was studying his Thucydides. He evidently was studying the ancient works, and this boar came up and attacked him, and so he took his book and stuffed it into the boar's mouth, and that was the end of the boars in Boar's Hill. So the story goes.
We talked about quantum mechanics in the second part of the book, but we haven't gotten to the third part of the book. And
the fantasy.
The fantasy, right?
Well, you see, initially it was aimed, I think, most specifically at what is a current, very important part of current cosmology, which I don't happen to believe, but it is that in the very early stages of the universe, very, very tiny fraction of a second, 10 to the minus 36 or 10 to the minus 32 seconds, between that kind of area, it's a stage, right at the beginning, there was this incredible exponential expansion where this tiny little universe became hugely larger by many, many powers of 10. And this is supposed to explain various things, such as the uniformity we see and so on. Well, I don't believe it explains that. All sorts of reasons that it doesn't explain that. You need something. It doesn't work for that. However, it does explain certain things which are hard to account for otherwise. So it's become part of, from a good theory. So that was the fantasy. Well, there were other crazy schemes as well, not just inflation. Others which are regarded as crazy by other cosmologists, but the inflation is part of the standard picture. But the irony is that since when it was about 11 years ago when I gave my lectures on this topic, and now, in the middle of that period, I have my own crazy idea, you see, which is that the universe, okay, the conventional picture, Big Bang is the beginning, inflationary phase, I'm not having that, but that was then, and then the universe had a more sedate expansion, and now it's beginning to accelerate in its expansion. This is an observed thing, which got the Nobel Prize a couple of years back. Now, I'm accepting that picture. However, I'm saying that that is only what I call one eon of a continuing succession of such things. So the remote exponential expansion is something which becomes the Big Bang of the next eon. Now, you see, that's a crazy idea, because how can something big and cold become something very tiny and hot? Well, it's because, according to the scheme, there's nothing around, both at the very late phases and the very early phases, which have any mass. And if you don't have any mass, you can't build clocks. And if you can't build clocks, you can't have the scale of size and time is indeterminate. And so that in this very remote stage, the physics doesn't know whether it's big or small. That's a funny idea, but it has many implications, some of which really seem to be there, although I'm having a lot of trouble convincing the conventional cosmologists. You see, because you might think, this is a crazy idea, how do I know if there was ever an eon before ours? So instead of inflation, you have this exponential expansion of the previous eon. In a sense, it's before the Big Bang, not after it. So that's the difference, you see. It's not like inflation, where you have this exponential expansion immediately after the Big Bang. But, okay, how could you have any observational evidence for the previous eon? So I began thinking, well, what's the biggest, most violent thing I can think of. You see, apart from the Big Bang itself, the most violent thing I can think of is, well, you see, our galaxy has in its center a supermassive black hole, which is about 4 million times the mass of the sun. This is pretty good evidence that it's there. We are on a collision course with the Andromeda galaxy. Okay, it'll take many thousands of millions of years, but we're still on a collision course. It has a much bigger black hole in its center, about 20 times as big. And when we collide with it, which is believed to be the case in a few thousand million years, these black holes are quite likely will capture each other. Not certain on the first, if they don't, then there'll be a second run. But I mean, they'll probably go through, the galaxies will go through each other and then come back and probably settle down. And eventually these black holes will spiral around into each other, swallow each other up, and there will be one unholy explosion. That explosion will be in the form of mainly gravitational waves, that's ripples in space-time itself. But they will carry away an absolutely stupendous amount of energy in a very short period of time. And this signal is something that we, if that happened in the previous eon, we should see evidence of it. And exactly what evidence it would be, it's a bit of a subtle effect. You should be able to see rings in the cosmic microwave background. That's the radiation that well detected and a big feature in modern cosmology, this radiation which came from the very early stages of the universe. And slight variations in the temperature contain all sorts of signals, most of which people are very interested in, but they're not interested in looking for these circular features which I claim would be there. And there does seem to be some evidence that they are there, although we're having a little trouble convincing people about it. And the thing is that once you get in a cluster of galaxies, you see you'll get galaxies colliding and other galaxies colliding, and so these bursts will happen several times. It won't just be one. So you would see rings in this cosmic microwave background, several of them with the same center. And this center would be where that previous eon galactic cluster was. And so we look for concentric sets of rings, and there's a Polish group which looked in a completely different way, and they also found evidence. When I say we, this is, I have an Armenian colleague, Vahe Gurzajan, who's been doing the analysis on this. But we've been looking at the more recent data, and we see similar signals. And we looked at the old data, and this is more recent data, and we still see these signals.
That was part of your talk as well in Kyiv when you were...
Yes, I'm sure I talked about it then. Yeah, that's right. So this is, you see, that the irony is that whereas I'm saying a lot of these ideas are fantastical, and here I come along with my own fantastical idea. So I'm now saying that fantasy is not such a bad thing after all. I mean, there's so much going on which is really weird in one way or another. I mean, we know quantum mechanics is weird, but there are, I mean, the Big Bang is weird. I mean, where did it come from? What's it doing? And so this is a theory of not just what's it doing, but why was it of this very particular character which it had. I remember Stephen Hawking making this claim very clearly, and I would have said the same thing. Namely, that the Big Bang, okay, that was a singularity. The whole idea of space and time sort of lost its meaning. So the very notion of before doesn't make any sense. So to ask the question of before is a meaningless question, you see. Well, I'm saying, okay, no, it's not meaningless, and you can't give a meaning to that. And then what was before the Big Bang was a previous eon. And the details of what was going on in that are reflected in the nature of the Big Bang. So
there was no beginning.
There was no beginning in this picture, yes. Well, you see, it has something in common with the old steady state model, because there was a time when I was getting really interested in cosmology, when I was a young graduate student, just starting in Cambridge, or when I was in London before that. There were some lectures given by Fred Hoyle on the radio, which were wonderful. But this was all in this, it was the first time I heard of it, the steady state model, which was that the universe expands, yes, that's true, but there was all the time creation of matter, very, very thinly dispersed over the whole universe, but enough that as the universe expanded, it would replenish the matter, and it would be in the form of hydrogen, which would then collapse into stars, and you get new stars, new galaxies, and then they would go expand out off the picture, and then you get new ones. And this had a lot of appeal. It's interesting that you look back at some of the great scientists, Newton in particular, who believed that the universe had somehow to be replenished all the time in some way. He didn't quite know how. Einstein, who tried to have a model universe which was static. He didn't like the idea of the expanding universe, and he produced this static model. And there's an irony there too, because he had to introduce this term into his equations called the cosmological constant, which he thought was a great mistake, because he needed to have the static model. And then it became obvious, from Hubble's data and so on, that the universe was actually expanding. So Einstein, oh dear, I made a mistake, I shouldn't have put that term in, I was wrong. And then it turns, in all the cosmology books, and then people see, well, it's actually there. He was right all the time, all along. But his model wasn't right. But nevertheless, the cosmological constant, which is now evidenced in this exponential expansion that is observed, is a key thing for my model. I need that. If that weren't there, and it took me a long time to believe in it, I may say, so I was pretty slow in picking up on that, even though when the observations showed it, I thought, well, maybe it's dust and there's some other explanation. But then I got convinced it was probably right.